Begin. Hello everyone, this is Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So today we'll go over the contents of week 9. Before that, we'll discuss some questions from week 8 from the assignment that was there last week. And then we'll move on to week 9. Okay, so let's begin. So just to recap for the questions that are shown to you in week 8. So we studied static stability for the first 6-7 weeks of this course. So static stability was defined as the inherent ability or inherent tendency of any body to go back to its equilibrium. For an aircraft, it was the inherent ability of the aircraft to go back to equilibrium. It was the inherent tendency. Okay. So what were the conditions for the 3 directions? The first one, for the longitudinal case, the only condition for static stability was that Cm alpha should be less than 0. Okay. Then for your directional case, the condition was Cn beta should be greater than 0. And for your lateral case, Cl beta should be less than 0. Cm alpha, I think we've discussed several times why it should be less than 0. Cn beta, we'll just go over it once. So if this is your fuselage reference line, this beta, is this positive or negative side slip? Beta, if this is beta, is this your positive or negative side slip angle? Your positive side slip angle. So this is positive. So for a positive beta, that is if it encounters a gust, if it encounters a wind in that direction, you want to negate, you want your stable aircraft to negate this disturbance. How do you do that? You turn the aircraft in the direction of your beta. So if it has an inherent tendency to regain its equilibrium, which direction would it turn? It would turn towards beta. That is, it would yaw to the right, correct? It would yaw to the right. So this is the Cn that it should produce for static stability, for directional static stability. Now, is this Cn positive or negative? It's moving about your z-axis. Z-axis is vertically downward. Use your left hand thumb rule and tell me if the Cn is positive or negative. Put your thumb in the direction of the z-axis. The direction your fingers curl is the positive. That's the convention. So is this Cn positive or negative? It is positive. So for a stable aircraft in the directional case, for a stable aircraft, for a positive beta, it should have a positive Cn. Therefore, your Cn beta, which is nothing but dCn, dCn by d beta, should be greater than 0. That is, for a positive change in side slip angle, you should have a positive Cn. Okay. Similarly, for your lateral case. Now, if it encounters a positive gust, right, positive beta, it should counter that moment. So if it encounters a positive gust, it should counter that moment. Okay. So positive gust, it has a tendency to roll right, but it should counter the moment. Your Cl beta should be less than 0. It's in the other direction. So your rolling axis would be the x-axis. Put your thumb in the x direction. The fingers curl towards your right. So that is your positive Cl. But you want it to roll to the left. So you need to have negative Cl. Okay, so Cl beta is L by d beta should be less than 0. Here L is the rolling moment. Okay, do not confuse it with the lift. All right. Then we moved on to dynamic stability. So these were the equations that were derived for a point mass system, right? So this was a point mass system in the 2-dimensional case. So it moves only in the x and y direction. And you had 4 equations here. The first equation gave you the variation of velocity. So it was v dot. Next equation gave you the variation of gamma. Gamma was what? What was gamma? What is gamma? V dot. It gave you the variation of v dot. Then it gave you the variation of gamma dot. What is gamma? Second equation gives you the variation of gamma dot. What is gamma? Gamma was? It's an angle. Which angle is that? Let's draw this aircraft. Horizontal. Flying in this direction, so you want to bring the velocity is here. So what is gamma here? Alpha is the angle of attack. What is gamma? What is gamma? Flight path angle. It's this. This angle is gamma. So your second equation gives you the variation of this gamma, right? So it gives you the rate of change of flight path angle. Next equation, what does that give you? Gives you x dot. And this is y dot. So this is for a point mass system in two-dimensional case, okay? So it moves only in the xy plane. Here you have 4 equations. If you introduce the third direction, that is z direction, you will have 2 more equations, right? So you will have a total of 6 equations, all right? For a point mass system. Okay, next, let's look at this. Now for the longitudinal case, let's look at the dynamic stability equations, right? Till then we had only static stability. Till now we had only static stability. So how did you write your CL? Your linear approximation of CL. Here CL is the CL is coefficient of lift. Okay. So till now we had only CL equals CL naught plus CL alpha into alpha for the static case. Now that the dynamic equations have come into play, dynamic means where the time comes into consideration. Okay. So the rate of change with respect to time. Okay. So now you have some other terms. You have Q, your pitch rate Q, your rate of change of angle of attack alpha dot, and you also had delta E. CL delta E into delta E. So initially you had CL is CL naught plus CL alpha into alpha. Then we introduced some control surfaces. In this longitudinal case, it is elevator. So then you introduced a term CL delta E into delta E. Now we have some dynamic terms, that is Q and alpha dot. Okay, Q is the pitch rate and alpha dot is the rate of change of angle of attack. Now, all of these other terms are non-dimensional. CL, CL naught, CL alpha. CL alpha into alpha is non-dimensional. Okay, so how do we get this other term also to be non-dimensional? Because pitch rate has a unit. What is the unit of pitch rate? Unit of pitch is radians, which is non-dimensional. What is the unit of pitch rate? Rate of change of the pitch angle. What is the unit? What is the unit? Radian per second, right? So Q is radian per second, which is not non-dimensional. So to make it non-dimensional, we introduce some terms just to make it non-dimensional. Okay, so we have QC by 2V. That 2 is just one convention that we follow, but you can do away with it, but ensure that it's retained throughout. But in this case, we are using the 2. Okay, so is this non-dimensional? QC by 2V. What is C? Mean aerodynamic chord. What is V? Meter per second. So velocity. So is this non-dimensional? It is non-dimensional, right? So you have meter per second, and then you have Q is meter per second gets cancelled, correct? This is non-dimensional, which is why you have this term. It's not just CLQ into Q. So what is CLQ? If this has to simplify, what is CLQ? What is CLQ? dCl by dQc by 2V. Only then this term will be valid, right? Similarly, you have Cl alpha dot. Again, alpha dot unit is radian per second. So you need to non-dimensionalize it. Okay, so you have Cl alpha dot is dCl by d alpha dot c by 2v. We are non-dimensionalizing using the same terms. Okay, so which is why you have this thing. All right. So this is your linearized equation for the dynamic stability in the longitudinal case. Similarly, you have for your moment. This was for the force, you have for the moment. Just like in the case for the lift, initially we had only Cm naught and Cm alpha into alpha. Then we introduced a control surface, and then you got Cm delta E into delta E. And now we have two new terms because of the dynamic stability. You have pitch rate Q and you have alpha dot, rate of change of angle of attack. Okay. Now, due to this pitch rate, there is a change in angle of attack. There is an alpha, delta alpha. So that is given to you by this equation, where LT is the moment arm. Okay, so you increase pitch rate, that moment arm. Okay, now because of this pitch rate, because of the increase in angle of attack, there is an increase in lift. So there is a delta L. Similarly, because of this increase in lift, will it produce a positive or negative pitching moment? This is happening at the tail. Okay, so if I have an increase in lift at the tail, will it produce a positive or negative pitching moment? Just think about it. So if this is your tail, so if you start a reference line and you have increased delta L, this is your CG, it produces this kind of a pitching moment. Is that positive or negative? So it's pitched down, it's nose down. Is that positive or negative? Negative, right? It's giving you a negative. Pitch down is negative. That's our convention, which is why you can see that the delta M that it's produced due to a pitch rate, it has this negative sign. Okay, that is the reason it has a negative sign. Now, using these delta L and delta M, we have found out the coefficient. So CLQ and CMQ, both of them, we have found out. Okay. Then, so does everyone remember this equation? Mx double dot is Cx dot plus Kx is equal to Ft. What is that equation? What does it represent? It's one of the first equations that we study when we start differential equations. So what does this equation represent? Spring mass damper. Exactly. So this is a second order ODE, represents a forced spring mass damper system. Okay. So now this is similar to our dynamic stability equations. How? Let's see. Let's look into it. So we have, let's take X. X is similar to or analogous to alpha, right? X is analogous to alpha and X dot is analogous to Q or alpha dot. Alpha dot is, we've taken Q as what X dot represents, okay? So if we take these two terms, so what are C and K? So K, the equation has Kx. What is K here? K is the stiffness coefficient, right? So in our equation, what would K be? If we've taken X to be analogous to alpha, what would K be? Cm alpha. So K would be similar to Cm alpha, which is like intuitively you understand, right? So Cm alpha is like the stiffness. It gives a resistance or it resists the disturbance acting on the aircraft, right? It's just like the stiffness. Okay. So then next, what do we have? C. C. What was C? In the spring mass damper equation, what was C? It was damping coefficient. So if your X dot is analogous to Q, what would C be analogous to? It would be CmQ. So Cm alpha is analogous to the stiffness coefficient or something that represents stiffness or resistance towards disturbance. And CmQ is the damping coefficient, is analogous to the damping coefficient, right? So what it does is that it tries to bring the body back to equilibrium over time. It damps the disturbance, right? So that is how you relate it to your spring mass damper system. Okay. So here it says this Cm alpha is like the stiffness coefficient, which provides the resistance towards or the ability to bring it back or resist any motion that causes disturbance from the equilibrium. Okay. So it's the stiffness. CmQ is like the damping coefficient that tries to bring back the body to equilibrium. That is, it tries to dampen the motion equation. Okay. So now if CmQ is negative, it tries to bring it back. Right. So that is what it represents here. Okay. Now let's go to the next slide. Okay. So what are the forces that are acting on the aircraft? What types of forces? What types of forces act on the aircraft? We've been talking about forces acting on the aircraft, motion, and all of that, right? So what kinds of forces act on the aircraft? What kinds of forces? We have three types of forces. We have aerodynamic, gravitational, and propulsive. So what are the aerodynamic forces? This we have dealt with extensively. So what are the aerodynamic forces? Aerodynamic forces. What different aerodynamic forces have we studied? Throughout the course, we've done several of these, right? So what are the different aerodynamic forces? You have lift and drag. So these depend on your V infinity. What is the gravitational force? What could be the gravitational force? The weight, right? So the weight of the body. What is the propulsive force acting on the aircraft? What is the propulsive force acting on the aircraft? It's the thrust, right? Right? Fairly simple. Okay. So, and then we have two frames of reference. We have the inertial frame of reference and the body reference frame. Why do we need two frames of reference? Why do we need two frames of reference? Why do we need two frames of reference? Why do we need inertial and body? Or give me a reason for any one of them. Why do we need inertial or why do we need body? Why do we need any of these reference frames? Why do we need the body fixed? It should be body fixed. Why do we need the body fixed reference frame or why do we need the inertial reference frame? We use both of these reference frames for our study. Why do we need both of them? Or why do we need any one of them? In which frame do Newton's laws of motion work? In which frame do Newton's laws of motion work? In the inertial frames. Correct? That is fairly basic. So we need to know the values in the inertial reference frame in order to use the equations, like Newton's laws of motion, Euler's equations of motion. So we need to know the values in the inertial reference frame. Why do we need body fixed frame? How do we measure different quantities on the aircraft? The velocity, the forces acting on the aircraft, the angles. In which frame do we measure all these? How do we measure it? In which frame do we measure it? All these measurements are in the body fixed frame, which is why we need that frame. So all of your measurements, all of your quantities come in the body fixed frame, and we need to use it in the inertial frame, right? So we need to rotate it to the inertial frame. Okay. So before that, let's just look at the equations of motion. So F equal to ma, Newton's laws of motion, Newton's law of motion, right? You know that equation, F equal to ma. You expand it to get this, right? And since it is a rigid body, since your aircraft is a rigid body, this quantity goes to 0. Okay. Then you have this last equation where this is in the inertial frame. And since you know your quantities only in the body frame, you employ this transport theorem or this transformation from the body fixed to the inertial frame. So we'll just try deriving this in a while. Then you have similar equation for moments, right? M equal to this equation. Again, since we have a rigid body, this quantity goes to 0. We're left with this, and again you have something in the inertial frame that is represented in the body frame that is converted into the inertial frame. Okay, how do we go about doing this? How do we convert any vector from its body frame to inertial frame? How do we do that? Okay, let's have a look. So let me just erase this. Why am I not able to do this? Just a minute. Let me try to figure this out. Why am I not able to erase it? Okay, but I'm still unable to erase it. One second, just give me a minute to figure this out. Sorry about that. Um, why is this hanging? Zero. Just turn on to zero. All right. Okay, sorry about that. So, okay, so let's take any vector A. Let's represent it first in the inertial frame. Okay, so let's assume its components to be AX I cap plus AY J cap plus AZ K cap. In the same vector, when you represent it in the body frame, it will have different components. Okay, so it's the same vector, but it has a different component. So if I take IB, where it is the body frame unit vectors, we have AY JB and AZ K. Okay, so it's the same vector represented in the inertial and in the body frames. Okay, now let's take its derivative in the inertial frame. So let's do dA by dt in the inertial frame. Okay, so here what we have is we take dAx by dt I cap. You should, if you do employ the chain rule, you have sorry, you should have a ax di by dt, correct? Employing the chain rule. But since your I, J, K are the inertial frame unit vectors, they are fixed with respect to time. So there is no such derivative. Di by dt does not exist. Okay, so this is zero. So you have next, you have dy by dt j cap. And similarly, you have ay dji by dt, which is zero. And then you have daz by dt k cap, az d k cap by dt. This goes to zero, correct? Now let's take the derivative in the body frame. Okay, so now let's do a by dt in the body frame. What do you get? This is in the body frame. Okay, dAx by dt IB, then dAy by dt JB, plus dAz by dt kb. Here, since these unit vectors are fixed to the body and not with respect, not in the inertial frame, the body frame will move with the body. It's fixed with the body, right? So its unit vectors will move when the body moves. So you will have a derivative. So you have plus ax dib by dt plus ay djb by dt plus az dkb by dt. Now, what is the rate of change of a unit vector? So if I just do dib by dt, and if your body is moving with an angular velocity of omega, what would this value be? What is it equal to? Rate of change of a unit vector of a body that's moving with an angular velocity of omega. What would the value be? What would the value be? It's just omega cross the unit vector, right? So it's just omega cross IB. Similarly, you have it for JB and KB, right? So if I do dJB by dt, we have omega cross KB and BKB by dt is omega cross KB. Okay. Now, if I plug this into this quantity, what do you get? dA by dt is dA by dt in the body frame plus omega cross A vector, correct? So this entire thing is omega cross A vector. All right. So that is how you obtain this relationship. Any vector differentiation, the rate of change of any vector in the inertial frame is given by the rate of change of the vector in the body frame plus omega cross the vector. All right. So this is the derivation for it. Okay. Now let's look at some of the terms. Okay, this is messy here, but we have force, velocity, omega, moment, and h. Okay. So all of these terms are what is represented, what needs to be represented in the inertial frame to complete our dynamic stability analysis, to use those equations. Okay, so all of these quantities will employ this conversion from the body frame to inertial frame because all of the measurements are performed in the body frame. All these quantities are known to you in the body frame. How do you measure velocity? U, V, W. Is it known in the body or the inertial frame? When you measure the velocity from the aircraft, is it measured in the body frame or inertial frame? Measured in the body frame. So you'll have to convert all of this into inertial frame to employ these equations of motions. Okay? Okay. Now let's look at the questions. So for an aircraft to be directionally stable, which of the condition is true? Directional stability condition. We had begun this discussion with this question, with the answer to this question. We had begun this class with this discussion. Right? So what is it? What is it? For a positive beta, should your Cn be positive or negative? For a positive beta, should Cn be positive or negative? just repeat it. I think not everyone was here. Okay. So if this is your fuselage reference line and it's encountered with a crosswind, so this is your beta. Correct? So how will you, if the aircraft is stable, so what will CN be? It should produce a restoring moment in this direction, right? So Cn should be positive. So dCn by d beta should be positive. Okay. Next question. A negative value for Cl beta will result in rolling moment that rolls the aircraft towards the direction of side slip, away from the direction of side slip, towards the direction of pitching angle, away from the direction of pitching angle. Which would it be? Which one would it be? So side slip, again, consider positive side slip. If your Cl beta is negative, will it roll towards the side slip or away from the side slip? Towards side slip or away from side slip? Tell me. So let me just try to do this. If it rolls, so for a positive beta, which is the same as the previous case, right? So this is positive beta. It's roll. Positive beta means your aircraft is disturbed in the right direction. You need it to roll back. So you point your finger towards the positive x-axis, right? So your positive roll is this. But you need a restoring moment. You need Cl to be, you need a negative Cl, right? That is when your Cl beta, you understand? So if your Cl beta is negative, if your Cl beta is negative, it will roll away from the direction of side slip, right? So for a positive beta, you have a negative roll. If your Cl beta, dCl by d beta. For a positive beta, you have negative Cl. That is what it means when they say negative value of Cl beta, correct? So if you have a negative rolling moment, it will roll in this direction, correct? So that is rolling away from the side slip. So the answer is away from the direction of side slip. Okay. Next question. Which of the following statements is or are true? The first one, CLP is pitch damping derivative. CMQ is usually less than 0. CM alpha greater than 0 means the aircraft is stable. Aircraft is unstable. Which of the following is or are true? What is CLP? Is there any such term? Did we study CLP? Did you study any such term, CLP? No. So CLP is the pitch damping derivative is false. What is the pitch damping derivative? Which is the pitch damping derivative. CLP does not, we have not studied that, right? So there is no such term. Look at the next questions. Next option. CMQ is usually less than 0. Is that true? We had discussed this when we just saw the equations for delta L, delta M due to pitch rate. Right? So is CMQ positive or negative? Usually. We had just seen these equations. Yes, here CMQ is positive or negative. It's negative, right? So the statement B is true. This is false, B is true. CM alpha greater than 0 means the aircraft is statically unstable. True or false? In the longitudinal sense, what is the only condition for stability, static stability? What is the only condition for static stability? CM alpha should be for longitudinal static stability. What is the condition? CM alpha greater than or less than 0. I think we begin every lecture with this discussion, with this statement. And I had repeatedly mentioned that this would be very crucial. So we have dealt with this and we know this. So CM alpha should be greater than or less than 0 for static stability in the longitudinal case. I don't think I'm going to discuss this point again. So I'll give you another minute or two to tell me if CM alpha should be greater than or less than 0, and hence if statement C is true or false. How was your CM versus alpha curve? CM versus alpha or CL, how was it? Did it have intercepts? Did it have slope? What was the intercept? What was the slope? What was the sign? Tell me, CM alpha, the curve, the slope. Something like this, right? So CM alpha should be less than 0. That means CM alpha greater than 0 gives you stable or unstable aircraft. unstable, right? So the statement is true. So both B and C are true. Let's go to the next question. A particle whose mass is 5 kg moves in the xy plane with a velocity of 4.3 meter per second I along the line y equal to 5.7 meters. Find the angular momentum L about the origin when the particle is at 11, 5.7 meters. So this is your xy coordinate, correct? So how do you go about doing this? What is the equation for angular momentum? L is R cross P, correct? We know this. And what is P? P is mv. V is given to you. What is R? R is also given to you. What is R? The position vector. What is R? Where is the particle at this moment? It's at 11, 5.7. Right? So it would be 11 I cap plus 5.7 j cap. Correct? So now you have all of your equations. Can you solve this? I'll give you a minute or two to solve this and then we'll do it together. Okay, let's do this now. So let's find out P. P is 5 into V. So it's just 5 into 4.3 I cap. So that gives you 21.5 I cap. Okay. So now let's do L. L is R cross P. How do you go about doing this? Just okay. R is 11, 5.70, and P is 21.500. Perform the cross product. How much do you get? You get minus 5.7 into 21.5 K cap. How much is that? Let's multiply this. minus 122.55 K cap. So this is the option, correct? Is that clear? Yeah, okay, let's go to the next question. Now on the same particular force of minus 4.1 Newton I cap is applied to the particle. Find the torque in Newton meters above the origin due to this force as the particle passes through the point 11 and 5.7. It's the same point. Okay, so the position vector is the same. So position vector is 11 I cap plus 5.7 J cap. Okay. All right. How do you find out the torque? What is the equation for torque? Angular momentum was R cross P. What is torque? R cross F, right? So just find out the cross product and tell me. I'll just give you another minute to find this. How do you find this? Just find out and tell me quickly. It's coming to 23.37 K cap. So this is the answer. All right. Next question. An arbitrary vector A in rotating frame B, rotating body frame B, having an angular velocity omega, can be represented in inertial frame by. We just derived this. So what is it? We just derived this. This, right? We just derived it. I'm not going to derive it again. You can just go to the lecture and see. Okay, next question. Okay, the unit data for question 7 to 9. The wing lift curve slope CL alpha wing is 5.2 per radians. Horizontal tail lift curve slope is CL alpha T is 3.5 per radians. Mean aerodynamic chord is 3.08 meters. Wing area is 87.79 meters square. Horizontal tail area is 21.65 meters square. Tail moment arm is 14.02 and the tail efficiency factor is 0.9. They've asked you to find out a tail volume ratio VH. What is the formula for VH? We have a direct formula. ST LT by SC. Now all the quantities are given to you directly. Substitute and tell me the value. Direct substitution, just put it up 21.65. The moment arm is 14.02. The wing area is 87.79. and mean aerodynamic chord is 3.08. Can you just tell me the value quickly? Just calculate it. I don't have a calculator. So I'm getting 1.12. All right. Correct me if I'm going wrong anywhere. So I'm getting the value of 1.12. The next question, calculate the value of lift coefficient due to pitch rate, CLQ. Again, you have a direct formula. What was the formula? So CLQ was 2 eta VH CL alpha tail. 2 eta VH CL alpha of tail. So let's just substitute and do it directly. Eta was 0.9. VH we just calculated as 1.12. CL alpha tail is 3.5 per radians, and they've asked you also in per radians. So no need of any conversion. What is the value? Just calculate and tell me. So I'm getting 7.056. So that is this. Again, correct me if I'm making any calculation mistakes. Okay. Calculate the value of pitch moment coefficient due to pitch rate. Now earlier we had lift coefficient, now we have pitching moment coefficient. Again, it's given per radian, so no need to convert anything. What was the direct formula? CMQ. What is the formula? Minus 2 eta VH CL alpha tail LT by C. Minus 2 eta VH CL alpha tail LT by C bar. Notice that there's a minus sign there. Do not forget that. So let's just substitute it. 2 eta was 0.9. VH was 1.12. CL alpha tail was 3.5. LT was 14.02. And C bar 3.08. Let's calculate this and let me know. So it obviously has a negative sign. All of your options have the negative sign. What is the answer? I'm getting minus 32.118. So this one. All right. Okay. Now let's look at some other questions. Okay. So if force of I plus 3Jn is acting on a particle located at the vector position R, 3I plus 5J meters, what is the torque about the origin? similar to the question that we just did. Okay, can you do this? I'll give you about 2 minutes to do this. We just found out the torque, right? So just try doing it. Okay, so torque we know was R cross F, right? So both of these vectors are directly given to you in this question. So you have R is 3I plus 5J cross I plus 3J. Let's do a quick cross multiplication. JK 3501330. Just do that, you get 4 K cap, right? Positive 4 K cap and Newton meter. Positive 4 K cap. Okay. Along similar lines, let's do if a force F, same force and the same position vector, what is the torque about the point having coordinates 0 and -6 meters? How do you do this? The force and the position vector are the same, but now they've asked you torque. In the initial case, they'd asked you the torque about the origin. Now they've asked you torque about another point. How do you do this? Torque is still R cross F, but what changes? What changes are brought about into this? There they've asked you about origin, here they've asked you about some other point. Torque equation is still R cross F, so what changes? So torque is R cross F, right? In this case, our position vector changes. Initially, position vector with respect to origin. Now, position vector has to be shifted towards the new point. So, if your new point, oops, just a minute. Yeah, so if your new point is 0, I minus 6j cap, you need to do R from the new point, okay? So R minus P cross F. Do you understand this? Is there a doubt here? So all position vectors that we've taken are measured with respect to origin. Now they've asked you the torque about a different point. So you subtract that point. So now your position vector has to be from the new point, right? So your original vector, your original R vector minus your P vector, okay? So RP, let's just take P properly. One second. So your R vector was 3 and 5, something like this. And P is 0 and minus 6, somewhere here. This is your P vector. This was your R vector. X, Y. Right? So now you subtract these two vectors and multiply with your take cross product with the force. So how do you do this? So it's 3 minus 0 minus 5 minus of minus 6 j cap cross F. So you have, what do you have? 3 I cap minus 11 j cap cross I plus 3j. Can you tell me the value of this? Take the cross product and tell me. It's just I j k 3 minus 11, 0, 1, 3, 0. What is the value? Minus 2 k cap and value is Newton meter, right? So it is this one. All right. Now let's try another question. The position vector of a particle of mass 5 kg is given as a function of time. R is 6I plus 5tj. What will be the angular momentum of the particle about the origin at time 10 seconds? How do you do this? Angular momentum H is R cross P. We saw this in the first question, right? First assignment question. Okay. R cross P. How do you find out P? P is mv, Newton's law of motion. Now what is V? R you have, P we didn't have, so we did this. Do we have V? We don't have V. How do you find out V? How do you get the V vector? If you have the position vector, how do you find out velocity vector? You have the position vector. How do you find out the velocity vector? I'll give you a moment to think about this. Try solving it and then we'll do it together. let's do this now. So V is the rate of change of position vector. Okay. So it's just R vector dot. So dr vector by dt. And R vector is 6i plus 5t. This is your R vector. Okay. So now if you differentiate with respect to time, you only get 5j meter per second. Plug that in here to get 25j, correct? Kg meter per second. And this value, you plug it in here. You take the cross product. So it is 6i plus 5 2j cross 25j. What is this value? You get 150 k cap joule second. Right? So it doesn't depend on time. Because of the cross product between ij and j, it doesn't depend on time. So at any time, the angular momentum will be 150 k cap. Okay. So this is the value, 150 k cap. All right. Now look at the next question. Okay, so if they ask you at some time 20 seconds, what is the value now? Here it was 150 k. Here it will be again, it will be 150 k, right? Because it doesn't depend on time. We just saw that. So the final value doesn't depend on time. So it will be 150 k for any time interval or any time duration. Okay. Okay. Next question. Non-dimensional value for change in lift coefficient due to pitch rate is CLQ. What is CLQ? So your CL equation we had seen was CL naught plus CL alpha into alpha plus CL delta E into delta E plus CLQ into QC by 2V. Correct? QC by 2V. Then you had CL alpha dot, you had alpha dot C by 2V. So now the question is, what is CLQ? So it's DCL by what is it? Just from this equation, you should be able to get it. We had done this before, but just from this equation, you should be able to get it. B QC by 2V, correct? It is this option. Why is it not the third option? Because you have another parameter here. A, it doesn't become non-dimensional, then it is not B. Okay, here there is a where did these equations come from? This fx, fy, fz. We just expanded this equation, correct? So you have terms Vc. Vc is here. So dVc by dt, you will have terms u dot, v dot, w dot, right? So that is here. You have u dot, v dot, w dot. And then you have omega cross Vc terms, right? So you have omega is what? Is P QR and Vc is UVW. So you will have these product terms, PU, PV, such terms. So you can see all of these terms in this equation. Now, what is all of this equal to? It's equal to the sum of the forces in 3 directions. What forces act on the aircraft? We have just seen this. What are the 3 types of forces that act on the aircraft? 3 categories. Look at this equation. Try to remember the previous slide. Just tell me 3 categories of forces that act on the aircraft. So you have your aerodynamic, propulsive, and gravitational. Correct? You have these 3 categories of forces. Then you have the 3 equations of motion, the moment equations, LMN. Where do we get these equations from? Again, when you take this and expand it. So you have dH by dt. What is H? It has Hx, Hy, Hz, which have terms Ixx, Iyy, the moment of inertia terms. Okay. So the final equation will have terms that have Ixx, Iyy, and it'll also have omega cross H. So omega is what? PQR. So you'll have PQ times Ix, such terms. Okay. So you can see that here. Right. So these are the 6 equations to describe the equations of motion of an aircraft in 3 directions. Fx, Fy, Fz, Lmn. Force, moment. Okay. Then what we saw in the lecture was one way to represent orientation, which was Euler angles. What were the Euler angles that we discussed in the lecture? Psi, theta, phi. Okay, and in this very particular order, which is a convention that we follow for aircraft. Psi, theta, phi. Psi is about z-axis, theta is about some y-axis, and phi is about x-axis. Now we need to see that you must not confuse your psi with the yaw. Okay, this psi is different from yaw. The psi is the rotation about ZE axis. What is ZE? ZE is the inertial Z axis. ZE is fixed in time and space. ZE is the inertial reference frame, Z axis of the inertial reference frame. Okay, so the rotation about the inertial Z axis is xi, not yaw. Do not confuse it with yaw. The Euler angle xi is different from yaw. Similarly, the Euler angle theta is different from the pitch angle. Okay, how is it different? First, you rotate this inertial reference frame by an angle psi about z. Then you get some new axis, right? You get ZE, x1, y1. Then if you rotate about the new y1, you get theta. Okay, that is your Euler angle theta, not to be confused with pitch. Okay, so this is just one way of representing orientation. There are several other ways. You have something known as quaternions, something like quaternions, and there is modified Rodriguez parameters. Do you know what these are? So Euler angle is one way of representing orientation. You have quaternions and MRPs. So MRP, modified Rodriguez parameter. Okay. So these are 2 other ways to represent the orientation, and you also have your direction cosine matrices, which you know. So the problem, the disadvantage with the Euler angles or the DCM, direction cosine matrices, is that when there are large angle changes, for example, if it is in the case of a satellite, you have angle changes greater than 90 or 180 degrees. At such conditions, these representations, that is Euler angle and DCM, encounter singularity. To avoid these singularities, you have other formulations like quaternions and MRPs. Okay, but for the aircraft, we use Euler angles and we use it in this sequence: psi, theta, phi. Okay, now where do these angles come into play? It only comes into play in the FGX, FGY, FGZ, which is the gravitational forces. Why? Because all of the properties are already measured in the body frame, right? So these properties are measured in the inertial frame, and when you rotate it, you have these theta, phi terms coming into play. Another place where it comes is the PQR representation. What was PQR? PQR was omega, right? So another place where these Euler angles come into play is the omega. Okay. Now let's look at some questions. For the rotational matrix R given below, what are the values of xi and theta? So our typical or conventional rotation was, I told it was xi, theta, phi. Xi about z, theta about y, and phi about x. Right? So what is the final rotation matrix? R is Rz psi, Ry theta, and Rx of phi, where Rz, Ry, Rx are the principal rotation matrices about each individual axis. So sir had dealt with these extensively. Do you remember these three matrices? So let me help you remember. Let me write down Rz and in terms of phi. What was the matrix? It was cos psi minus sin psi 0, sin psi, cos psi 0, 0, 0, 1. Okay. Similarly, what was it for Ry? By writing it down for Ry and Rx, and then multiply the three of them to find out the rotation matrix. Try doing this. Just write down for Ry and Rz. I'll just give you a couple of minutes to write down. I'll give you a couple of minutes to write down for Ry and Rz. Okay. So Ry was what? In terms of theta, cos theta, 0, sin theta. 0, 1, 0, minus sin theta. Correct me if I'm going wrong somewhere, okay? Cos theta, correct? What about Rx? There's no place to write Rx. Okay, let me just Rx 5. How do you do this? What is the value? Rx 5, 1, 0, 0, 0, cos phi minus sin phi, sin phi, 0, sin phi, cos phi. Is this right? Correct me if I'm going wrong somewhere, okay? Try to remember these three and now multiply these three. So you multiply and get this value. So you will get a large matrix, and then you equate it to this given rotation matrix to find out a theta and psi. Okay. So just multiply these three. I'll give you a couple of more minutes to do that. Just multiply these three and we'll see. if you multiplied, you would have gotten this matrix, right? So these are the three matrices that we had written down, right? So RZ, RY, and RX, right? So if you multiply it, you get this large rotation matrix. Now, how do you go about doing this? So you see here your sine theta, compare it with this. So minus sine theta equals minus 0.7071. That means for any such value, you have theta is minus sine inverse R31. That is the third row, first column. So this is the formula. But you can see that if you do the sine inverse, you get two theta values, right? So theta 1 is this, and theta 2 is pi minus theta 1. This also gives you the same value for sine. So you get two possible values for theta. Okay. So for this case, let's do these two. What is sine inverse R31 minus sine inverse R31? What value do you get? What value do you get? Minus sine inverse 0.7071. You get pi by 4, right? Okay. Now if you do pi minus pi by 4, how much do you get? 3 pi by 4. Okay. So you know that two values for theta. You got your two values for theta. Now let's move on to psi. How do you do psi? Now if you divide R21 by R11, if you do R21 by R11, you get tan psi. Correct? But what is the problem with this? It depends on, it will be positive or negative depending on the value of theta. Right? If theta is in the first or the fourth quadrant, it's simple. You get the value of psi directly. But if it's in the second or third, it will be the negative. So one easy way to go about doing this is that you take psi is tan inverse R21 by cos theta by R11 by cos theta. Okay, so if you do this, then you will be able to get the sine value correctly. Okay, so now let's do it for case 1, for theta 1. For theta 1, what is psi? Psi 1, what is psi 1? Just substitute the value there, R21 by cos theta and R11 by cos theta. Tan inverse R21 by cos theta by R11 by cos theta. R21 is what? 0.5. R11 is also 0.5. Should be very simple. Just do it fast. What is psi? First value of psi? Is pi by 4. Correct? Now let's do it for the second value. For theta 2. What is psi 2? Just substitute it. Do tan inverse and tell me what is the value. Get minus 3 pi by 4. Correct? If you check the quadrant, you get minus 3 pi by 4. Correct? So what is the correct option? Two values of theta are pi by 4 and 3 pi by 4. And you have pi by 4. So this is the correct answer. Okay. So with this, I think we can conclude today's session. Do you have any questions? If there are no questions, then we can end the session here. We'll meet again next Tuesday. All the very best for your assignment. So see you Tuesday. We'll end the session here. Thank you.